Welcome to this session. In this session, we are going to discuss about the second shift property for Laplace transforms. We'll start by defining the second shift property and then illustrate it on a sketch or on a diagram, and then finally do an example to see how it's applied. So let's see. So the second shift property states that if the Laplace transform of a function f of t is given by capital F of s, then Laplace transform of the product of two functions f u of t minus d times f of t minus d is given by e raised power minus sd times capital F of s for any constant d greater than 0. So some remarks or notes on this theorem. One, that the function u of t minus d times f of t minus d is obtained by moving the function u of t times f of t to the right by an amount d. So let's illustrate this one on a diagram. What's happening here? So just a sketch. So shifting of the function u of t times f of t to the right by an amount d. So this is how this can be illustrated. So if we have so this is a t-axis, this is a t-axis. Now on the first graph, this is the u of t times f of t axis, while on this other one is u of t minus d times f of t minus d. So if we have this as the function, then you have the same function shifted by an amount d to the right. So this is graph A, this is graph B. That this new graph is obtained by shifting it by an amount d to the right. So from this origin, we have d steps to the right to obtain this new function, u of t minus d times f of t minus d. Now, another thing to note is that since f of t is defined only t greater than 0, then f of t minus d equals to 0 for t less than d. So whenever this value here is less than 0, then the value of the function of the Laplace value of the function will be taken to be 0. Now, another thing to note on this one is that u of t minus d is redundant since it is necessary for inversion of the Laplace transform. So this will be seen in later lectures, how to find the inverse Laplace transforms. So let's illustrate how to apply this second shift theorem or second shift property to some two problems. So example 1, given Laplace transform of function f of t is given by 2s over s plus 9, find the Laplace transform of u of t minus 2 times f of t minus 2. Now, so we see this one directly from the definition of the second shift property, that since when L of f of t, the Laplace transform of a function f of t equals to f of s, then Laplace transform of u of t minus d times f of t minus d is given by e raised to power minus s d times capital F of s for d positive. Here we have d equals to 2. Just relate t minus 2 by t minus d. So d will be 2. So this implies that Laplace transform of u of t minus 2 times f of f of t minus 2 will be given by e raised power, so d is 2, so be minus 2s times capital F of s. Now we know capital F of s from the question. Now since capital F of s is usually the same as Laplace transform of f of t, given by, in this case, 2s over s plus 9, then the Laplace transform of u of t minus 2 times f of t minus 2 will be given by e raised to minus 2s times 2s over s plus 9. I'm simply replacing this capital F of s by this formula. So which will reduce to 2s e raised to minus 2s divided by s plus 9. So this is what we get for that particular problem. Another example. Example 2. The Laplace transform of a function is e raised to power negative 3s divided by s squared. So this is an arbitrary function. So find the function. Now, the existence of an exponential term in the Laplace transform signifies the application of the second shift property. So solution, we say the exponential term e raised to minus 3s in the transform, in the Laplace transform, suggests that the second shift property or theorem is used. Now let e raised to minus s d times capital F of s be this given transform. So let's have that one as our final solution for the transform according to the second shift property. Then clearly d is 3 and capital F of s is 1 over s squared. So if we let, or we know that Laplace transform of f of t equals to f of s equals to 1 over s squared implies that t or f of t is actually t. That's what we saw in the first session, that if you get the Laplace transform of a function f of t equals to t, then its Laplace transform is 1 over s squared. So therefore, this is the f of t. So hence, f of t equals to t, and f of t minus d equals to f of t minus 3. So this is what we have. Now, using the second shift property, or theorem, Laplace transform of u t minus 3 times f of t minus 3 should give us Laplace transform of u of t minus 3, and then the f of t minus 3, the answer is t minus 3 as obtained from here. So which is actually, this is given by f of t minus this, f of t minus 3, and if f of t is given by this one, then f of t minus 3 must be t minus 3. So this is t minus 3, which is e raised power minus 3s over s squared. Hence, the required function is u of t minus 3 times t minus 3. For this f of t minus 3. Now we can illustrate this on a diagram. So if this is the f of t axis, and then this is the t axis, this is f of t, then we have such a thing. So where this is 3. So now that is how f of t will be given by u of t minus 3 is a function times t minus 3. So this is actually the required solution. Thank you.